Assalamu alaikum wa rahmatullahi wa barakatuhu. Friends, welcome back to my channel. In this session, we will discuss relationship between VCC, feedback, currents and signals in any SMPS IC, in any PWM controller IC. To understand the function of these parameters, I will use datasheet for UC3842 IC, that is 343, 344, 345. and UCC28742 IC. These both ICs are primary side regulators. VCC or VDD. VCC are chip voltage or biasing voltage for any IC, any integrated circuit. Why we say VCC, any IC, when it is using transistors? That means we need common collector voltage. Here are transistors, so it needs VCC voltage, common collector voltage. The word VCC will give us idea that it is transistor based IC. If any IC is using MOSFET, MOS technology, as we see here in its output stage, it is using MOS technology, MOSFET. That means we need drain voltage. So that is the reason it is named VDD voltage. This lecture will help us to understand the relationship when any IC is fluctuating. The SMPS controller is not driving full load. Let's suppose we need 10 watt and it is providing just only 4 watt. It is not providing enough current in the output stage. These ICs are used in hot area. There is no optocoupler. At feedback pin, the same auxiliary voltage are connected at this pin. It will provide feedback current at this pin, so it will regulate the output voltage. The drawback in this circuit that it will provide approximately 5% regulation of the load voltage, and it has slow response to detecting load transitions. If there is no load, it is working normally, it is regulating the voltage, but at sudden load, it will not sense that load immediately. So it has slow response. But if we have optocoupler based feedback network, when the output voltage are maintained in the output, we receive feedback. As soon as the voltage will drop, it will provide feedback to the IC that voltage are dropped. Using this technique, 2% regulation can be achieved in the output. 2% tolerance is acceptable, and it will detect load transitions fastly with compared to primary side feedback network. Now if we see this sample circuit of UC3842 IC, when we apply voltage to the rectifier, the voltage are rectified and smoothing capacitor will regulate the voltage. It will remove the ripples. That DC voltage are provided to this transformer winding one end. Second end is connected to this MOSFET drain pin. Source is connected to this resistor and this end is connected to ground. So we can see positive voltage that are stored here and its ground side is connected here. So current will flow in this path if the MOSFET is on. If the MOSFET is off, then there will no current flow in the circuit. That means we need some signal to turn on this path, to close this switch. For that purpose we need drive signal from this IC. It is driving the gate. These voltage are provided to transformer. We need some working voltage for this chip, for this IC. That voltage will turn on this circuit, its internal circuitry, to provide a smart control to maintain the signal here, to control the output voltage. Because there is no any power source to turn on this chip. For that purpose, a startup resistor is connected between positive line and ground. There is RC network. This point is connected to VCC pin. This is IC 300 volt DC. Now this resistor will allow current to charge this capacitor, because when capacitor is empty, it will work as a short circuit. It will draw more and more current until the voltage will build up at this pin. Because it is working in primary side, it will not start switching immediately. Let's suppose voltage are building at this pin, at same time it is receiving voltage at this 7 number pin. This capacitor is charging. If it will start immediately, there will a sudden load on the DC rail. Because voltage are low, that may cause overcurrent condition or some other situations. To prevent it, a delay time is provided for charging this capacitor. Outer capacitor that is connected at this pin and ground, and here is startup resistor. There is UVLO switch, under voltage lockout switch. It will receive voltage and it will send this voltage to the output transistor, but it will not allow to turn on this circuit until the voltage are reached at specific limit. This circuit is biased up with few microamperes. If you see its data sheet, 2842 or 2844 IC, minimum 14.5 and maximum 17.5, nominal 16 volt. At 16 volts, it will turn on this section. Before 16 volt, at this pin, this circuit will remain off. It will consume only 0.3 milliampere current. That is startup current. 0.3 milliampere, that means 300 microampere. When 300 microampere current is flowing in this circuit, it will start this capacitor slowly. This is current, these are voltage. When we connect to the line voltage at 0.3 milliampere, it will charge the capacitor, VCC capacitor. When it will reach at 16 volt, it will draw this current from this line. When 16 volt are maintained here, it will turn on its 5 volt reference circuit. When 5 volt reference voltage are provided, and it will provide these 5 volts to its internal circuit. Same voltage are routed to the RTCT components, timing resistor and timing capacitor. It will start switching, it will start oscillation. While receiving 16 volt, it will provide 5 volt and it will turn on this circuit. When reference voltage, reference logic is good, the 5 volt are good, that time it will enable the output circuit. It is just only 50 milliampere. If any load, any component connected outside, either a small capacitor is leak. If it is exceeding then its limit, this pin will drop and this IC will turn off. This is good. Internal biasing circuit is providing voltage to the chip. It will start switching. When it will start switching, it will provide pulses to the MOSFET, to the transistor, IGBT, whatsoever there. It will allow to flow this current in the primary. When it started switching, the chip current will increase up to 17 milliampere. That is operating supply current. 12 to 17, and we will consider the upper limit. That means 17 milliampere current can flow in the output stage within this IC. That means this source is providing just only 300 microampere for charging. And now if there is no other source that can provide the required current, voltage level at this capacitor will start to decrease, because now this is working as a battery, so it will start to discharge. If you cannot find any other voltage, this voltage will start to decrease. When this level at this pin will decrease, then its threshold, minimum operating voltage after turn on, that are 10 volt nominal, minimum 8.5, we will consider the typical range, and the voltage will drop less than 10 volt. What will happen? It will turn off reference circuit. It will provide disable signal to the output flip-flop. This chip will turn off. When it will turn off, this path will again start to charge this capacitor in this way. This is that condition when it is switching, the chip is active. Maybe this MOSFET is not good, current will not flow. This resistor is not good, current will not flow. If this transformer is damaged, current will not flow. Or this auxiliary winding that will provide induced voltage. When it is switching, it is generating magnetic field. This magnetic field will provide voltage in the secondary side, and it will also induce voltage in this winding. So these voltages are rectified, and these will fulfill VCC current. Now, due to any reason, we cannot find this voltage. This winding is damaged, VCC diode is damaged, or any track is damaged, or this transformer is not switching, we will not find this voltage. At that time, voltage will reach at 16 volt. It will start switching, IC will work. When the voltage are reached again at 10 volt, it will turn off. When it will turn off, again charging. So it is called UVLO thresholds. This is starting, this is stopping limit. But normal voltage after power on, maximum 34 volt can be applied to this chip. Above than 34 volt, this clamp will clamp the voltage. So we can say the working window is above than 10 volt up to this limit. But startup for this IC UC3842 and 44, these voltage 16. If we discuss 3843 and 45, startup voltage are 8.4 and stop voltage 7.6. 42 and 44 are starting at 16 volt, but 3843 and 45 will start at this level in this region. The working currents are same, 0.3 milliampere standby current or startup current, and operating current 12 to 17 milliampere. It will drive the MOSFET gate. Normally one cycle is considered like this: turn on time, turn off time. This IC will control this turn on time to control the switching of this MOSFET. When we will allow a small shutter to flow the current in this primary, it will create low magnetic field, less magnetic field. But if we will utilize more duty time to turn on, that time more magnetic field will there. We know the mutual induction in the transformer always bases on amount of magnetic flux. If there is low magnetic flux, low output voltage. If there is high magnetic field, high voltage in the output. So we are controlling the flux, magnetic field in the transformer by controlling this turn on time. When this signal is connected to this gate, this base, current will start in this winding, but here is transformer. We know the varying current in the inductor will cause to increase the inductive reactance, because inductor always opposes to the change in current. We can say IL, inductor current, will increase in this way, linearly. Initially it will allow some current, but then it will increase gradually, linearly, because it is opposing to the changing current. Based on this ramp, the current will flow in this path. The same amount of current will cause to drop voltage in this resistor that is connected to the source pin. We can say how much current is flowing in this MOSFET and transformer that is causing to drop voltage in this resistor. These voltage are provided to I sense pin, that is current sense pin, that is this one. If any time the current will increase than a specified limit, that time it will turn off the output stage to protect the circuit. Let's suppose 1 ampere current is allowed in this circuit, in this primary winding. At 1 ampere, let's imagine that 1 volt will drop here. It will reach to I sense pin. There is a current sense comparator. If we see one side, one pin is connected to 1 volt reference. That means if there is any pulse arriving more than 1 volt, will trigger this comparator. It will trigger PWM latch. So it will hold this latch and it will turn off the output. In simple words, if current here will increase due to any reason, if the circuit was working good and this resistor value is slightly increased, before this, if the actual circuit was providing 1 volt at 1 ampere and its resistance is increased, maybe at 0.5 ampere current, it will provide 1 volt. That will cause false switching for this IC. The circuit is drawing just only 0.5 ampere, but its feedback network, current sense circuit, is not working properly. It is providing false output to trigger this IC into leading edge blinking. In leading edge blinking, this IC turns off the drive signal. That means this circuit will not provide enough power. If it is designed for 5 volt 2 ampere 10 watt, maybe it will provide 5 volt 1 ampere. The output current will decrease. If we have some circuit that is not providing a required output wattage, that time maybe we need to consider this circuit. Current sense circuit, maximum 1 volt. Maximum input signal 1 volt. If any time while switching, let's suppose this is inductor current and same time the voltage are increasing at I sense pin. If it is switching in this portion, maybe we will find this pulse. 0 volt, 0.3 volt. If due to any reason, if this pulse will reach to 1 volt, this IC will turn off the output. This is one condition, that current sense signal is providing false input. When we are switching, the voltage are transferred in this winding and this winding. At initial startup, positive voltage were derived to these resistors that are startup resistors, and these are charging this capacitor, that is VCC capacitor. But now when the circuit will start, that time this winding will provide voltage to this capacitor, and now this winding is capable to provide above than 17 milliampere current, that is operating supply current 11 to 17 milliampere. In the second data sheet it is saying 12 to 17 milliampere. When this circuit will start, it will maintain voltage above than this limit, in any portion. That will depend on the duty cycle, that will depend on the load size, because it is flyback transformer. In turn on time, it will store magnetic energy in the core, in the primary winding. When this MOSFET will turn off, that time this stored energy will be transferred in the output side and in this winding. If it is providing slightly high voltage, VCC current limit resistor is used here. If you are receiving slightly more voltage, we calculated the circuit to provide 16 volt, but it is providing 40 volt. The voltage can be dropped by calculating the maximum required current, that is 17 milliampere. A resistor value will be connected here. Now when the voltage are maintained in the output side, a feedback signal is provided to TL431 reference signal. When it will receive 2.5 volt between ground and reference pin here, 2.5 volt, it will allow cathode current. It will turn on this path. When it will turn on this path, this optocoupler LED will turn on and it will send light to the phototransistor within that optocoupler IC. It will connect this reference voltage to the feedback pin. Between feedback pin and compensation pin, there is a compensation resistor. So it will receive 2.5 volt. Why? Because in this chip there is a biasing supply for the non-inverting input of this feedback comparator that is providing 2.5 volt. That means it will keep increasing the duty cycle, this time from minimum to maximum, until it will receive 2.5 volt at this pin. It will utilize maximum duty cycle to turn on the output transistor, the output MOSFET, to flow maximum current to find these voltage at this pin, feedback pin. When it will receive 2.5 volt at this pin, it will lock the duty cycle at that stage. In any condition, the voltage dropped here will cause to stop conduction of this TL431. It will turn off the optocoupler LED. This optocoupler LED will turn off this transistor. In result, feedback pin voltage will change. The voltage will drop here because we stopped a path from here and now it is connected to ground side. So voltage will drop. When voltage will drop, it will increase duty cycle again. So it is linear conduction. If the voltage will increase, that time it will provide more voltage above than 2.5 volt, so it will decrease the duty cycle. When it will receive 2.5 volt and its gain is adjusted properly from the compensation pin, this operational amplifier will work. It will provide reference for this current sense amplifier. Now when the voltage are maintained, same time it will monitor the current sense signal. Let's suppose in this channel current is flowing and we are receiving 1 volt. That means maximum allowed current is provided in the winding. But the second condition now, due to any reason, due to overload, due to failure of this section, if this network is unable to send a light here to provide 2.5 volt at this pin, now the current is at maximum limit. The feedback is missing. It will utilize maximum duty cycle and the voltage will drop at VCC pin at this level, at UVLO, under voltage lockout threshold. That VCC pin is dropped, then this threshold, the IC will turn off and it will wait until the voltage are reached again at this level. So it will try to find feedback voltage, but waiting for feedback. If the current sense signal is reached at highest level, the IC will stop its function. It will work in leading edge blanking mode. So this is datasheet of UC3842. Now we will see this IC. UC3843 and 44 ICs are very commonly used and simple ICs, but this UC28742 IC has more safeties, protections. If you see VDD pin, UVLO, under voltage lockout switch is working between 22 volt and 7.7 volt. 3842 IC was working between 10 volt to 16 volt, but this IC will work between 22 and 7.7 volt. A large range here. When initial startup voltage are above than 22 volt, it will turn on its power management and fault management circuit. It will turn on. It will provide 5 volt biasing or a reference voltage to the chip. Chip is enabled now. There is current sense circuit, feedback sense circuit. There is VS, voltage sense signal. It will sense line voltage and it will sense over voltage protection signal. VS pin is connected to auxiliary winding voltage using voltage divider network. It is working as a zero crossing detector. The function is approximately same. Startup resistor will provide biasing voltage to VDD capacitor. VDD pin. When it will reach above than 22 volt, it will start to switch. When it is switching, it will provide drive signal to this MOSFET. When current will flow in this channel, in the primary winding, it will sense the voltage at this pin, voltage dropped across this resistor. Current sense is directly coupled with feedback. How much voltage are in the output and how much current is here. 3842 IC, there was 1 volt reference. Here is VCST. It is also similar function. So it will monitor 2 units at the same time, feedback and current sense. That time, if current sense is reached at its peak limit, it will provide leading edge blanking signal. The same way it will turn off the output signal. If current sense signal is above than 1.5 volt, this OC current fault circuit will generate error. It will generate error and it will provide to this IC. And if VCST signal is above than the limit that is added here, that time it will turn off the circuit. When it will turn off the circuit, it will provide 120 millisecond delay to reset the circuit, to reset the fault condition. If feedback is missing, over current, over voltage, if VDD voltage are above than the limit, above than the zero crossing level, that time it will generate fault, that there is overloading condition in the output. If there is overload condition, because it is flyback transformer, in the off time when voltage are being transferred in this winding will cause to increase voltage in this winding as well. So if there is any spike, that spike will reach here and this IC will generate over voltage condition. That fault is due to load spikes, OV fault. So maximum 38 volt and allowed voltage supply range is 9 volt to 35 volt for this chip UC28742 IC. Its running current, that is 1.8 milliampere. If we are discussing 3842, that is 17 milliampere, but its maximum limit is 2.4 milliampere. When this IC is in wait state, VDD are under 20 volt because 22 volt is threshold. Less than 20 volt, it is in waiting state. Maximum current is 115 microampere. And when circuit is working and it is locked for 120 milliseconds as a fault condition, it will consume 2.75 microampere. VDD turn on 21.6 volt, maximum 24.5 volt, we can say 22 volt, and lower limit 7.8 volt. When the power supply is off and we inject power, it will not turn on until the voltage are maintained above than 22 volt at VDD pin. If the VDD pin voltage are dropped less than this limit, this IC will turn off. Feedback input voltage maximum 1 volt at 23 microampere. Feedback pin maximum 1 volt. In that IC there was 2.5 volt, but here 1 volt. When 1 volt and the feedback current is 23 to 30 microampere, it will intimate the circuit to create switching, and switching frequency is 100 kilohertz. VCC, the first startup, then working voltage. Feedback will intimate the circuit that the required voltage are maintained in the output. Current sense signal will intimate that the circuit is obtaining maximum allowed input current in the primary side. So these parameters will work together. If any parameter is out of limit, this IC will not work properly. I hope this video is informative for you. If it is good, give a thumb up. If you have any question, please write in the comments. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.